complex numbers, and complex numbers are imaginary numbers that are not real, but they are a thing. So the first we're going to talk about is right here. So you can actually square root a negative. And the square root of a negative 1 is a 1i. It's an imaginary number. So imaginary numbers are not real, but they are a thing. We're going to use them quite often here in Algebra 2. If we ask you to write your answer in standard form, that's where we're looking for something like this. The first piece is going to be your real number, and then the second piece would be the imaginary. So if we say standard form, that's all we mean is the real number is going to come before the imaginary. When we look at powers of I, we're going to see a pattern. So I to the first is just I, right, by definition. Now, I squared, I'm going to use the definition of I that we just had on the last slide. Remember that I is the square root of negative 1. Well, when I square that, that just gives me negative 1. So every time you see an I squared, that is equivalent to a negative 1. And that's a really important one that you're going to want to remember for this unit. So if I look at I cubed, I'm actually going to combine what I've already done. I'm going to look at this as an I squared times I. Well, I squared was negative 1. I is I. And the result of that product is a negative I. I to the fourth, I can look at a couple ways. I'm going to look at this as I squared times I squared. Well, I squared is a negative 1. And if I take that times itself, I'm going to get a 1. And so here's the first 4, and you're going to see that there's a pattern that follows after that. So I to the fifth, we can create this a couple of ways, but I'm going to look at it as an I to the fourth times I. Well, we just did I to the fourth, and that was 1 times I, which is I. I to the sixth can be constructed several different ways, but you're going to see that that comes out to be a negative 1. I to the seventh would be a negative I. And then I to the eighth would be a 1. So when you have I to a power, for every multiple of 4, it's going to follow this pattern. So when we evaluate something pretty large like I to the 50th, I want to think, well, what power or what multiple of 4 can go into 50? And that would be a 48. So I'm going to rewrite this. I don't know why my pen's not working here. As I, there we go, to the 48th. And then that would have to be times I squared. Well, because the 48 is a multiple of 4, I know that that's going to end up being 1 because the fourth number in my pattern is always a 1. And I squared is a negative 1. And so the product of those is negative 1. So I to the 50th is equivalent to negative 1. Now, in breaking down radicals with a square root, it's just like when or radicals with a negative. It's just like when they were positive. There's only one difference. So if this were a positive 90, you would have split it into 9 times 10. But because it's a negative 90, one of these numbers has to be a negative, and you always want to make the perfect square the negative, because now we know that we can square root negatives. The square root of negative 9 is 3i, and then I can't take the square root of 10, so 3i root 10 would be my result. For this second one, I would break this into a negative 16 and a 3. And the square root of negative 16 is 4i. Now remember that real numbers and imaginary numbers are not like terms. So this is as far as I can go. I can't combine a 7 with a 4i root 3. Those are not like terms in many different ways. So that's all we can do. Subtracting, It's just combining your like terms. With adding, those parentheses are just placeholders. So remember with standard form, the real number comes first. So I'm going to combine my real numbers. Then I'm going to combine my imaginaries. These are not like terms, so that's as far as I can go. Subtraction, it's pretty much the same idea, but I do have to distribute the negative and then combine like terms. So combine the real numbers, then combine the imaginaries, and that's all that I can do. Multiplying is a slightly different game, right? You can multiply unlike terms. So when we have something like this, we're going to distribute the 1, distribute the 2i, and we get something interesting here because if you remember from a few slides ago, I said I squared is something you're going to need to remember. I squared is a negative 1. So here in this last term, I really have a negative 8 times a negative 1, which essentially turns into a positive 8. So now combining like terms, I do have two real numbers to combine. 3 plus 8 is 11. And then I'm going to combine my imaginaries. And that's what I can do. You should never have an I squared in your final answer. If you do, you're not done yet. You have to simplify that I squared is a negative 1. All right, Grumpy Cat, talked about these several times, right? We cannot do these with rational expressions. We cannot do these with rational expressions. And then even in this bottom right corner, okay, several students have shown that they know that they have to multiply by the conjugate to get a radical out of the denominator. That's awesome. I think we have pretty much mastered that skill. The issue is the shortcuts, right? When I take this numerator times this numerator, I have to distribute. I can't just multiply the non-radicals and the radicals. That's not how multiplying by two binomials work. So be careful that you're not trying to shortcut your work and then it's not going to give you the right answer mathematically. And I bring that up because we're going to talk about division. Just like with radicals, you can't leave a radical in the denominator. Well, imaginaries technically are radicals. So I need to rationalize this denominator by multiplying by the complex conjugate. If this denominator is a 3 minus 4i, its conjugate would be a 3 plus 4i. And then I need to multiply binomial times binomial for numerator and denominator. So let's show that and see what we get. I don't know why it's not writing. So when we get to here, a couple of things happen. Well, these 12 i's cancel, but then I have I squareds. A plus 8i squared is actually the same thing as a minus 8. And then a minus 16i squared is going to be the same thing as a plus 16. So when I combine my like terms in the numerator, I have a negative 5 plus 10i. And then in the denominator, I'd end up with a 25. Now, all of these are multiples of 5, so I'm going to reduce by a factor of 5 to get my final answer, which would be negative 1 plus 2i all over 5. Okay. Now with this, just remember that this means take the binomial times itself 3 times. That part of my screen isn't working. Go down here. Now remember, when you're multiplying binomials, you can only do 2 at a time. So I'm going to do these front two. If I distribute well, this I squared is actually going to become a -1. Well, then when I combine my real numbers, they cancel. And I just have 2I times 1 plus I. So let's distribute that. Well, plus 2I squared really is a -2. And the last thing, we just have to make sure for standard form that real number has to come out front, followed by the imaginary. So that's how we cube a binomial that has an imaginary. Now let's solve. So we did this the other day, and these are very similar. Number one, the square root method is going to be your fastest. You can subtract 9 from both sides. Then you have to divide by 4. Now we're to where we can square root. And when you square root, remember you always have your plus or minus. And when you square root a fraction, I would always throw the negative up into the numerator, because the square root of a -9 is 3i, and the square root of 4 is 2. And that's going to be our final answer. We don't have I in the denominator, so we don't need to rationalize. So that's our answer. Positive 3i over 2 and negative 3i over 2. Number 2, there are a few ways that you can do it, but the fastest way is going to be the square root method. If I add 4 to both sides, I'm now able to square root. And I'd have it equal to plus or minus 3i. Now I can split into 2 equations here if I chose to, but I also know that everything on the left is a real number and everything on the right is an imaginary. So I can't combine any of these like terms anyway, so I'm going to keep it all as 1. And when I add 2 to both sides, I need to write the 2 first because it's the real number piece. And then I'm going to divide everything by 3. And I get 2 plus or minus 3i over 3. And that right there would be my final answer. So when you're solving quadratics now, if you do end up with a negative under the radical, it can simplify. Think about breaking down with your perfect squares, and then just don't forget your I.